Determine the efficacy of a metal organic framework for a specific mixture separation application. Transient breakthrough experiments are usually conducted in laboratory units with breakthrough tubes of diameters of approximately 5 millimeters. The length of the packed section may be, say, 100 millimeters. The volumetric flow rate at the inlet to the breakthrough tube is of the order of 2 milliliters per minute, and the superficial gas velocity of the mixture flowing through the tube is approximately of the order of 5 millimeters per second. To compare the separation performance of different MOFs, breakthrough experiments may be conducted to determine the productivities of the recovered purified product. As an example, I show here experimental breakthroughs for 1090 mixtures of propine, component 1, and propene, component 2, at a total pressure of 100 kilopascal and a temperature of 298 Kelvin. These breakthrough experiments are obtained with two different MOFs, CIF6 copper TPA and TIF6 copper TPA, shown by the red circles and blue triangles respectively. These experimental data are from these two publications in Angewandte Chemie and in Chemical Science. I give here the relevant information on the mass of adsorbents packed in the tube. For TIF6 copper TPA, 0.51 grams are packed in the tube, and the inlet flow rate is 4 milliliters per minute. For CIF6 copper TPA, the pack length is 0.05 meters, and the mass of adsorbent is 0.488 grams, with an inlet flow rate of 4 milliliters per minute. What is important is to have a MOF that has the highest productivity of purified propene. And if we demand that the propine content is less than, say, 40 ppm, we can use the experimental breakthroughs to determine the propene productivity, and a simple mass balance will show that the propene productivity is the molar concentration of the gas mixture at the inlet, C sub T, which is the total pressure divided by RT, CT times Q naught, which is the volumetric flow rate of the gas mixture at the inlet, divided by the mass of the adsorbent, and the integral from T2 to T1, where T1 is the breakthrough time for the, propine, and T2 is the breakthrough time for propene. So we integrate between T2 to T1, and this is the mole fraction of alkene in the gas mixture exiting the tube. And this is the integral with respect to the time. The integration can be carried out simply using, say, a simple Simpson quadrature formula, and the productivities of purified propene can be calculated. For CIF6 copper TPA, the value is 37.8 moles per kilogram. This is reported in the Chemical Science paper. And for TIF6 copper TPA, the productivity of purified propene is 25.5 as reported in the Angewandte Chemie paper from 2022. That's all very well. I asked the question, can we estimate the alkene productivities more simply by using the ideal adsorbed solution theory? IAST calculations of mixture adsorption equilibrium may be combined with a shockwave model for transient breakthroughs in fixed beds to determine the productivities of purified alkenes. As an example, let's return to the separation of 1090 mixtures of propyne and propene using the two MOFs TIF6 copper TPA and CIF6 copper TPA, blue and red. The shockwave model is an idealized case in which the concentration fronts traverse the column in the form of shock waves, and this model is described in two of my papers. The first one, RSC Advances 2017, the other one in ACS Omega in 2020. Readers may consult my papers for the derivation of the shockwave model. The shockwave model is shown here for the experiments with TIF6 copper TPA and for the experiments with CIF6 copper TPA. The salient features of the model are as follows. From the IAST, for calculations for a feed mixture with mole fractions Y10 and Y20 at the inlet. In this case, we have Y10 equals 0.1 and Y20 equals 0.9. We can determine from the IAST the component molar loadings in equilibrium with the partial pressures in the bulk gas mixture entering the adsorber, and the component loadings are respectively Q1 and Q2. Q1 is for propene and Q2 is for, I beg your pardon, Q1 is for propyne, component 1, and Q2 is for propene. The component loading Q1 for propyne is simply equals the mole fraction of propyne at the inlet, Y10, times the molar concentration of the gas mixture at the inlet, Ct, times the volumetric flow rate, Q0, divided by the mass of adsorbent, times the breakthrough time, T1. So from the shockwave model, we can use the IAST calculation of Q1 to determine the breakthrough time T1. During the time interval delta T, purified propene can be recovered, and the productivity of purified propene is given by this expression, delta Q equals Ct, total molar concentration of the gas mixture, times Q0 divided by mass of adsorbent times delta T. And this delta Q can be determined from the IAST calculations of Q1 and Q2, and this is the formula. So the productivities of purified propene can be determined from IAST calculations, provided we resort to the simplified shockwave model. The calculations of delta Q values for the productivities are respectively for CIF6 copper TPA is 36.2. This is shown here. I beg your pardon. And for TIF6 copper TPA, the productivity value is 31. For TIF6 copper TPA, the productivity determined from IAST is higher than the value determined from experiments. On the other hand, for CIF6 copper TPA, the productivity determined from the IAST is 36.2, whereas the productivity from the breakthrough experiments is determined to be 37.8, slightly higher. The reason for the higher productivities in the experiments is due to synergy between absorption and diffusion. But this is a rather special case. Generally speaking, the IAST calculations of delta Q provide an upper bound to the alkene productivities that are achievable in experimental units. Ethane feedstocks to the polymerization reactor needs to contain less than about 40 ppm of ethane in order to prevent poisoning of the catalyst. And the selective capture of ethane from mixtures with ethene is an important separation problem. And I show here experimental data published in Nature Communications in 2020 for 199 mixtures of ethane and ethene using ZUL100. Experimental data are shown here by the red circles. The productivity of purified ethene meeting the target purity, i.e. containing less than 40 ppm C2H2, is determined to be 134 moles per kilogram. If we adopt the simplified shockwave model for the breakthroughs, the productivity of purified ethene is given by the expression here for delta Q that was also introduced in the previous slide. This metric is termed the separation potential, and it's calculated from the IAST from the component molar loadings of components 1 and 2, Q1 and Q2, where 1 refers to ethane and 2 refers to ethene. Y20 is the mole fraction of ethene in the feed mixture, and Y10 is the mole fraction of ethane in the feed mixture. Therefore, for 199 mixtures, Y10 is 0.01 and Y20 is 0.99. The IAST calculations for delta Q, the separation potential, is 200 moles per kilogram. That is higher than the value of 134 moles per kilogram determined from the experiments, because the experimental breakthroughs have a distended characteristic due to diffusional limitations inside the pore structure of ZUL100. The separation potential is a combined metric that takes into account the uptake capacities of components 1 and 2, and also the selectivity for the separations. The absorption selectivity is given by this expression from the shockwave model. It's related to the delta T, which is the difference in the breakthrough times of components 1 and 2. The higher the selectivity, the longer is the time interval between breakthroughs. And if the selectivity is extremely large, then delta T tends to this expression Y20, which is the mole fraction of component 2 in the feed mixture, times the breakthrough time for component 1, which is the breakthrough of ethine. If the selectivity is unity, delta T is 0, and no selective separation can be achieved. The separation potential is a combined metric that reflects the combination of selectivity and uptake capacity, and is the appropriate metric for ranking MOFs in separations in which the desired purified product is recovered in the adsorption cycle. Consider the separations of mixtures of ethene and ethane to produce a purified ethene using a MOF JNU6CH3 that is selective to the saturated alkane mixture. The experimental breakthroughs are shown here by the blue triangles for a 50-50 mixture of ethane and ethene at a total pressure of 1 bar and a temperature of 298 Kelvin. The productivity of purified ethene, corresponding to 99.95%, can be determined from the experimental breakthroughs, and the productivity has been shown to be 22.06 liters per kilogram for JNU6CH3, as reported in this paper published in Chemical Science in 2023. It is instructive to compare these productivity values with the value of the separation potential determined from IAST calculations. Just to refresh our memories, the separation potential is derived on the basis of the shockwave model for transient breakthroughs in fixed bed adsorbers. In this case, the shockwave model is described by this cyan-colored lines here. This value of the separation potential is 1.06 moles per kilogram. That translates to a volumetric productivity of 23.7 liters per kilogram, obtained by multiplying this value by 22.4 liters per mole at standard temperature and pressure conditions. We see that the value of 23.7 is larger than the value of 22.06 determined from the experimental breakthroughs. The experimental breakthroughs have a slightly distended characteristics that results in a lower productivity of high purity ethene product that is recovered in the adsorption cycle. Again, it is worth repeating that the separation potential is the appropriate metric that reflects both selectivity and uptake capacity of mixtures. And delta Q calculations affords a simplified procedure for ranking metal organic frameworks for a separation application. We now consider the calculations of the separation potential for feed mixtures containing more than two components, as exemplified here for purification of hydrogen from mixtures with carbon dioxide, carbon monoxide, methane, and nitrogen. We consider separations using activated carbon, and the fixed bed adsorber operates at a total pressure of 2 megapascals and a temperature of 313 Kelvin. Hydrogen is the most weakly absorbing component and breaks through the fixed bed the earliest. The next in line to break through is nitrogen, followed by carbon monoxide, followed by methane, followed by carbon dioxide. So the purity of the recovered hydrogen in industrial practice, we demand purities in excess of 99.95% hydrogen. The purities of the recovered hydrogen is dictated by the breakthrough of nitrogen. It is wrong, therefore, to consider the purification of hydrogen as a separation between hydrogen and the strongly absorbing component carbon dioxide. Indeed, the purities are dictated not by the breakthrough time for carbon dioxide, but by the breakthrough of nitrogen. The separation potential in this case is given by this expression that is derived from the shockwave model, as I explain in my publications listed here. The IAST is used to calculate for the feed mixtures of the specified compositions here, where Q's are the component molar loadings of CO2, carbon monoxide, methane, and nitrogen. And this quantity is to be multiplied by a factor, that is the mole fraction of hydrogen in the feed mixture divided by 1 minus the mole fraction of hydrogen, which is the sum of the mole fractions of all the other impurities in the feed mixture. And this product is then subtracted with the component molar loading of hydrogen, which is practically negligible. So The sequence of breakthroughs is dictated by van der Waals interactions, and the separation potential here, given by this expression, is a convenient metric to rank candidate adsorbents for hydrogen purification.